In addition to talking about everything we did with waves, we also need to talk about how light relates to the concept of energy. To do this, we're going to use the fact that while light has some wave-like properties, it's also been discovered that properties of light can only be understood by describing the light as coming in packets of energy, which we call photons. So when we talk about the energy of light, we're going to be talking from the perspective of these particles called photons in many cases. So the amount of energy that one photon of light carries is directly proportional to the frequency of the light. So we represent this with this equation here. Energy, or E, so this is like E equals h nu. So the energy of our photon is going to be equal to these constant called Planck's constant times the frequency nu. As a reminder, this frequency here is measured in hertz, which is also the same thing as saying 1 over seconds, or you can write that as s to the minus 1. So for now, we're just going to say Planck's constant is a constant that we use a lot when we start talking about things like singular photons and energy. It helps us to directly relate the energy to the frequency. At a later date, if you stick with us in chemistry, we'll talk a little bit more about where this experimentally comes from and how we figured it out. But for now, we're just going to go with it's a constant. We use it. If you take a test or a quiz with me, it'll be available on the equation sheet you have available. Now, since it's related to frequency, it also has to be related to wavelength, since frequency and wavelength are directly connected. So the energy of a photon is going to be inversely proportional to its wavelength. So we represent this with E equals Planck's constant times the speed of light divided by the wavelength. Note again, you have to make sure that your units work out. So if your speed of light is in meters, your wavelength would need to be in meters as well. So make sure when using that to make sure those work. What this means is that while light has some wave-like properties, it can also be understood as being transferred in packets called photons. So photons are going to represent the smallest amount of light that we can have travel at once. We don't have half a photon. Light is always going to travel as a whole number of photons. This is where a term you may get also, we're talking about how it's particle-like here, but we've also talked about waves. You'll sometimes hear this called particle-wave duality. So particle-wave duality. What this means is that our light is going to act both like it travels like a particle, like you might imagine like a billiard ball that bounces off something, as well as a wave, like a water wave that goes through things. Because of this, some properties end up being understood better with one version or the other. And there are some questions, what does that mean it's with a particle and a wave? What we have the ability to tell you is that it does both of these things. We can't answer a question of why does it do both of these things, that we can't answer that for you. As you continue, again, this is a topic where light gets covered a lot in future chemistry courses as well, and we'll deal some more with some of what happens because of this particle-wave duality. But for now, we're okay with going with it can act like a particle and act like a wave, both at the same time, depending on things like how you're observing it and what types of information you're looking for. So now let's go back and take some of that information and work an example. So here, what is the wavelength of a photon that has an energy of 6.52 times 10 to the negative 19th joules? So for here, I'm going to use my equation E equals hc over wavelength. I'm then going to solve for wavelength at the beginning, and I'm going to do that by multiplying both sides by wavelength and dividing by energy. When I multiply by wavelength, this will cancel on bottom. So I'm going to multiply by wavelength and divide by energy. And I'll do the same thing on both sides so I don't change it. So on the left side, the energies cancel. On the right side, the wavelengths cancel. And I'm left with wavelength equals Planck's constant times the speed of light over energy. Now, this is in units of joules. Planck's constant is in joules. So I'm good on units there. And those are the ones that are going to have to cancel. So we're okay already. We don't have to worry about changing any units over. So I plug these numbers in. Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And we're going to multiply this by the speed of light, which is 3.00 times 10 to the 8th meters per second. We're then going to divide by the energy of our photon, 6.52 times 10 to the negative 19th joules. And you'll see that the joules will cancel here, and the seconds will cancel here, and we'll be left with meters, which makes sense. It's a unit of length. We multiply and divide all that out, and we're going to get 3.05 times 10 to the negative 7th meters. And for the way the question is worded, this is a good stopping point. If it had asked you something at the wavelength in nanometers, you'd have to do a further conversion, multiply it by 10 to the 9th, and see what it actually would be in nanometers. But for this problem, it doesn't ask us to, so we leave it in meters. Let's look at another example where you practice it this time. So what I want to know is, what is the frequency of a photon that has an energy of 2.43 times 10 to the negative 16th joules? So I suggest pausing it here and solving this question on your own. Hopefully you've done that, and now we can go to solving it. So we have energy equals Planck's constant times frequency. I want to know the frequency, so I'm going to divide by h on both sides, and I'll have that the frequency is equal to E over h. Note that I just flipped the sides because a lot of people like putting their variables on the left. You also could say that E over h equals frequency. That's a true statement too. I just moved the one variable to the left because it's easier to plug numbers in that way, but it didn't change anything about my problem. Just like if x equals 2, 2 also equals x. So what this leads to, I plug in my values, and I have that the energy of a photon here is 2.43 times 10 to the negative 16th joules. I then know that Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. My joules cancel, and if I plug all those numbers in, we'll get 3.67 times 10 to the 17th, 1 over seconds, which is the same thing as hertz, or s minus 1. And so again, it doesn't ask for a specific unit, so that would be perfectly fine. Now I just should check one thing real quick. Okay, yeah, I was making sure I did the rounding right, and I did. So 3.667, you round up the hundreds digit to 7 since it's above 5 for the next one. Okay. What if, on the other hand, we had multiple photons instead? So let's say we have a packet of light, and it has the whole packet of light has an energy of 2.50 times 10 to the negative 17 joules. And I also know that the light itself, I measure its wavelength, it is 9.80 times 10 to the negative 7th meters. I want to know how many photons are in this packet of light. So the way we deal with problems like this is we first solve the question of what is the energy of one photon of light, and use expand that to figure out what multiple photons would have. So let's say the problem had asked what would be the energy of a photon of this wavelength. Well, then you could just ignore this information. You don't need this yet. We don't need this yet, so we don't need it for the single photon case, because that is the total energy for a packet of light, and we want to know what the energy for one photon is. So we know, back from what we did with our worked example before, the energy equals hc over wavelength. And so we can plug our values in here, our Planck's constant. Okay, that's supposed to be a 4, and it should be up with the negative. I'm really bad at it. There we go. Yeah, you can see that's negative 34. The 4 is just kind of down. That's h. Then our speed of light is 3.00 times 10 to the 8th meters per second. We can see our seconds are going to cancel. And then we're dividing all this by our wavelength in this case. So our wavelength is 9.80 times 10 to the negative 7th meters. And this works because both these are in meters. If this were nanometers, you would need to convert it to meters first. So we plug this in and we get the energy from our equation is 2.03 times 10 to the negative 19th joules. So what makes this problem a little more challenging is it asks you to think about what is that energy equation related to. That equation is the energy of a singular photon. So what that means is that for one photon, you'll get an energy of 2.03 times 10 to the negative 19th joules. You may or may not notice, but what I like about this is, oh wait, I have this equal sign, and I have two different types of units. One is photons, one is joules. That would make this an excellent conversion factor, because we know that that means one photon over 2.03 times 10 to the negative 19th joules is a conversion factor. So when we solve for the energy of one photon, we can use that to convert between photons of a singular to multiples. So now this conversion factor could work one of two ways. We could tell you, oh, you have 200 photons, how much energy do you have? And then you put photons on bottom, have photons cancel, and multiply by the energy. Or in this case, you know the total energy. You want to know how many photons it has. So here we're going to have 2.50 times 10 to the negative 17 joules. And what we know is that for each photon, there's 2.03 times 10 to the negative 19th joules of energy for one photon. So our joules would cancel. And if we multiply that out, we're going to get that we have 123 photons. Here's a place where I would definitely round it to the ones digit no matter what it had actually told me, because I can't get something that, I can't have 123.2 photons or something like that. So this worked. We also could have done the reverse conversion. We could have found out that 123 photons multiplied by 2.03 times 10 to the negative 19th joules per photon provided energy of 2.50 times 10 to the negative 17th joules. So now let's look at how this is conceptually useful to us in a few ways. So to do this, we're going to talk about something we call atomic spectra. So we can make more of an application of this. So when atoms or molecules, we're mostly focusing on atoms so far, but molecules do this too. When they absorb energy, that energy has to go somewhere. In addition to this, that means because it's the atom or molecule absorbed the energy, it's going to want to get rid of it at some point. And when it does that, it also has to go somewhere. So this energy that it absorbed will often be released as light energy. Common examples you may have seen is fireworks or neon lights. So the wavelengths of any atom or molecule that it's going to release are going to be unique to that atom or molecule. And they're used like a fingerprint to identify the substance. So for example, if you've got hydrogen, it emits light that looks like this. It's got 4 distinct lines. We can define those wavelengths, and that shows that that atom must be hydrogen. We get things like this one way to do it is you can take a tube filled with hydrogen gas. You put a little bit of electricity into it. It'll glow because it's emitting the light that it's absorbing through the electricity, and we're able to see it. On the other hand, let's take another atom. Let's look at iron. Iron looks like this. Iron has a whole bunch of different wavelengths. So depending on the atom or molecule, it's going to have a different set of spectrums. And each of these are going to have specific wavelengths that are associated with them. So that can help us determine what an atom or molecule is based on that. And now, how do we think about this atomic spectra in terms of the structure of our atom? We're going to do this with something called the Bohr model. Now, I'm going to tell you up front, the Bohr model has some limitations in it. There are some assumptions it makes that we have later discovered aren't perfect, but for explaining atomic spectra, it's an excellent model to use, and that's why we're going to use it, but know that this is not a complete picture of how the atom functions and how electrons move. So what is the Bohr model of the atom? So Bohr developed this model to explain how the structure of the atom changes when it undergoes energy transitions. So why is it can only release certain wavelengths of light? Why does hydrogen release those 4 lines? Why doesn't it release other lines sometimes? It would seem reasonable if you didn't know any specifics about the atom that it should be able to release energy however it wants. So the main idea Bohr comes up with to help explain this is that the energy of the atom is something we call quantized. What that means that each atom can only release very specific amounts of energy. So when the electron wants to move from one energy level to another, there are set levels it could exist in. And the difference between those levels relate to how much energy can be released. So in the Bohr model, those electrons travel at fixed distances from the nucleus. And the energy of the electron is going to be proportional to the distance the orbit is away from the nucleus. So electrons can emit radiation when they leave their current orbit and travel from a higher energy level to a lower energy level. This emitted radiation is seen as a photon of light, and the energy that's the difference between the 2 energy levels when it jumps is the same as the energy of that photon. You may have noticed when we did those equations earlier, we can find the energy of a single photon of light. That will tell us then how much energy had to change between the 2 energy levels. That's why it's useful to find the energy of a singular photon. It can tell us the distance that an electron traveled to allow that photon to be released. This is a pictorial representation of what this looks like in hydrogen. So N represents different energy levels. We'll be talking about them in more detail in just a moment. And as the electron travels from these different energy levels, it releases specific wavelengths of light. So these 4 colors are wavelengths 410, 434, 486, and 657 are represented as those 4 lines that we saw earlier in the figure for hydrogen. So this model is helpful for us to explain how the emission spectra works, since if I know the distance it's traveling, I can tell you what colors should show up. The reason this model is incomplete is it doesn't account for the fact that the electron has some wave-like properties. It's still helpful, but it's not going to explain everything about how electrons move in the atom. With that, I hope you can see why we care so much about emission spectra, since if they act like fingerprints, they give us a really good way to look for what substance we're working with. So it has a lot of utility, and it also helps explain some of the properties, like why are they able to release light at particular wavelengths.